Hi all. Let us continue looking at variations of the Claisen condensation. In this video we'll look at the crossed Claisen condensation, or you could also think of it as a mixed Claisen condensation, because in both examples we are using two different esters. Now, the strategies we used previously to do crossed aldol condensations, those are the same strategies we're going to use here, and maybe you could use this as an opportunity to test yourself to see if you can apply what you learned with that crossed aldol to these two examples. Okay, I think the first self-test is, can you draw the product of this Claisen condensation without drawing the mechanism? Now, this strategy uses the idea that only one of these can form the enolate because only one of them has hydrogens on the alpha carbon. So that's your enolate, and this will be the carbon you're attacking. So let me draw that hint. You have a leaving group, right? Could you draw the product without having to draw the mechanism? Go ahead and pause the video while I recopy this and draw the product that I think occurs, and then we can compare. I have redrawn the reaction down here, and I put a couple of notations. I'm making a connection between the alpha and the dot, and therefore this is the bond that was made. Because we're attacking an ester, that's why we actually consider it a Claisen. It's really the ester that you're attacking makes it a Claisen, because here when you attack the carbonyl we do end up losing the leaving group, and don't forget the phenyl group or the benzene ring that's still connected to the dot. We double check because all Claisen condensations result in a beta ketoester, and also we just want to double check that our alpha carbon has two hydrogens. That was one of the stipulations to prevent the Claisen reaction from going reverse. Okay. Now, by this point, you should have seen and practiced several Claisen condensations. Why don't you pause the video and you're going to compare your mechanism now to mine when you come back. Okay, let's see how you guys did. The full mechanism is, just a reminder, that's our final product, a beta ketoester, and our mechanism is here. It is, as expected, the 5 steps, and you start out with making the enolate. So there's your enolate. You attack a carbonyl, but this time you don't attack another one of itself. You attack its partner, the one that cannot form the enolate. You have the O-, so you make the tetrahedral intermediate. You reform the carbonyl to kick out the leaving group. At this point, this is where it gets a little bit tricky. The leaving group is a base. That proton is still pretty acidic, so before you have a chance to separate it or isolate it, this will grab the proton and make the oxygen anion. So you're making another enolate. Again, if that hydrogen was not there, let's say we only had a hydrogen and a methyl group here, like that, then you wouldn't be able to make the more stable anion. Oh, and also the what do you call this? The weaker acid, right? This is a weaker acid than this. This is a pKa around 15.5. This is this one, the keto. The ester ketone. That is a pKa of around, oh boy, 11. Okay, so that's the driving force. And then you have to reprotonate to get to the beta ketoester again. So the tricky thing is for students is that you see the product, but unfortunately at this point you can't isolate it because you're under basic conditions, and you immediately grab that proton. and those are the reagents, so that makes sense. We protonate in the second step. Let's take a look at example 2. Again, it's crossed because we have two different esters, and in this case we're using a very strong base, LDA, and the idea is that's very strong and it will convert all of the ester into the enolate. Why don't you draw the product first, okay, and compare it to mine. Okay, the beta-keto ester I make using this ester and then these three reactions in sequence is this product right here. I do want to go over the mechanism because I do want to comment a little bit about that base, because you've heard me say over and over again the base has to match the leaving group. In this case it doesn't have to, because we can't do transesterification with LDA. You can do transesterification, right, with the methoxide or the ethoxide or hydroxide, any O- you can transesterify, but LDA you can't. And in the mechanism, once we have it drawn out, I'll explain why. But pause the video and go ahead and draw the mechanism for this set of reactions. Okay, the final product we're aiming for is this one right here. Ultimately, the bond, carbon-carbon bond that was made was that one. We expect 5 steps, as usual. And here we have LDA, lithium diisopropylamine, stripping off the alpha. We should label all the alphas. Stripping off the alpha hydrogen. Okay, and here we get our enolate. Now, what's different about this LDA is that it's very strong, but also the conjugate acid is a very, very weak acid. Take a look at those two pKa's. We're always favoring the side with the weaker acid, and therefore we have equilibrium favor the product side. That's different, right? That was actually different than this one, because that has a pKa of 15.5, which is higher than this one, which has a pKa of 25. So here we do create almost 100% of the enolate, meaning that we don't have any of this unreacted for this enolate to attack another one of itself. That's a huge difference, right, between using LDA and using a oxide base. We favor the right-hand side. But also, we cannot do any exchange of the leaving group because this is considered a bulky base, a crowded base. So it has a hard time actually connecting this N to this carbon to eventually kick out this leaving group. So there is no danger of kicking out this leaving group with the base. There is danger right up here. You know, if I had used ethoxide, right? If I had used ethoxide, where am I? Right here. There is a danger of that hitting this carbon, eventually kicking out this leaving group and getting transesterification. Okay, so LDA, there are two really good things about LDA. It's bulky. It's called a non-nucleophilic base. It doesn't act like an attacker. It just acts like a base. And also the conjugate acid is very weak, thus favoring nearly 100% of the enolate. Okay, now we're ready to go on. You attack the carbonyl. Some of you may say, well, that alpha carbon doesn't have two hydrogens. This is not the alpha carbon that we're interested in. Remember, it's the alpha carbon that is used to make the enolate that needs to have two hydrogens. Because we need that hydrogen here to drive the reaction eventually to this anion. Okay, so anyway, here we kick out the leaving group, and that leaving group is immediately going to grab this proton because this is pretty acidic, right? It has a pKa of 11. We get the anion, and then ultimately we have to have a second reaction to replace or to put back that hydrogen. And here we have our beta ketoester. That is the full mechanism, and again we have 5 steps. So whether you do this first example, crossed, or you do this example, another crossed, Claisen, you still have only 5 steps.